After the compound, the second kind of control structure that we look at is also a very important one. It's the conditional, which enables us to decide at runtime to execute one path or another, that is to say one path among a set of possible paths, two or more, depending on certain conditions that we evaluate at runtime. The basic form of the so-called conditional instruction, which is our basic conditional mechanism, is the following. It starts with the keyword if, followed by a condition, which is a Boolean expression. In the lecture on logic, we saw Boolean expressions. Then there's the keyword then a sequence of instructions, exactly what we studied in the previous sublecture, a compound, 0, 1 or more instructions, then the else keyword, then another compound, and a keyword end. As a general note, many of the constructs that we see, including control structures, have this general form of starting with a keyword, like if, then possibly several clauses, and ending with the keyword end. The initial keyword can change. We've seen if, we've seen do, we've seen a feature, and many we've seen class, many others, but the final keyword is always end to conclude such a structure. What is the semantics? That is to say, the effect of such a conditional instruction? Well, it's pretty straightforward. The execution of the construct will consist of first evaluating the condition. As a Boolean expression, it will yield true or false, and then as a consequence, the conditional instruction will execute one of the two compounds. The first one, if condition evaluates to true, and the second one, if the condition evaluates to false. So the conditional instruction's execution is always equivalent to exactly one of the executions of the two compounds given. This is the fundamental mechanism that enables us to take advantage of computers' abilities to take branches between their instructions at runtime, different branches depending on some condition that is being evaluated. Here's a typical example. It's very simple, but it's also important and typical. We have two numbers A and B, and we want to compute their maximum. Well, with a conditional instruction, we find out if A is greater than B. If so, max is going to receive the value of A. If not, max is going to receive the value of B, and you can see that as a result, max is going to have as its value the maximum of A and B. A and B could, and as a result, max could be integers. They could also be, for example, real numbers, or they could be strings, which are not numbers, but for which there is also a comparison operation greater than. In all cases, this little program extract, this conditional instruction, is going to compute their maximum. Note that it's not completely symmetric because we have made a difference between the case A greater than B and all the other cases, so we could have used A greater than or equal to B. This is how we write the mathematical symbol greater than or equal. Since we don't have this symbol on our keyboard, we write greater than or equal. So it would not have made any difference, because in the case in which A and B are equal, of course it doesn't matter which branch we take. It would be nice to have a fully symmetric instruction. Here it's almost symmetric. In terms of conditional viewed as a problem-solving technique, this is what we previewed in an earlier sub-lecture of this discussion of control structures. Conditional is a useful problem-solving technique when we have a problem that we can divide into two cases corresponding to two regions of the problem space, and we have a technique to solve a problem in each one of them, so we just combine them using conditional. A bit of syntax. The basic form is the one that we just saw. If condition, then instructions, else other instructions. It's also possible to have a form without the else part. The then part is always going to be there, but the else part can be absent. If we just write if condition then instructions, it's really an abbreviation for if condition then instructions, else what, else nothing. It's possible to have an empty compound. When we defined a compound in the previous sub-lecture, we said it's a sequence of instructions, but it can be any number of instructions, 0, 1, 2 or more. So it's not very useful to have an empty compound, but it can serve a purpose as here. But on the other hand, if it's in a conditional instruction and the else clause is empty, we just omit it completely. It's simpler to write just the form given above. Here's an example of the application of such a conditional without an else clause. Assume that we want to prepare a bill and we want to add a certain penalty if the bill is overdue. So we are going to write something like this. If date is greater than due date, then we compute the penalty and we add the penalty to the amount. The case in which date is less than or equal to due date is such here that we don't need to do anything special. We only do something when the condition is true, and otherwise we just proceed with whatever comes afterwards in the program. It's possible to have conditional instructions inside conditional instructions. In general, there's no limit on having complex instructions within other complex instructions. So that's also going to be the case with structures like loops and multi-branches that we're going to see next. Here we just have conditional instructions. So let's assume that I have a condition 1, and then if that's satisfied, I want to execute instructions 1. In the other case, if condition 1 is not satisfied, I want to see if condition 2 is satisfied. Then, in that case, I will execute instructions 2. If condition 2 is satisfied, and of course condition 1 was also not satisfied before, I want now to test for a condition 3, and so on. So you can see that I'm writing smaller and smaller because I want everything to fit on the slide, but of course on a computer you cannot write smaller, but you see the general structure. We are going to wrap certain constructs inside of other constructs. The technical term that people use here is nesting. We nest instructions, in fact complex instructions, in this case conditional, within other instructions. Well, it's possible, but in the exact case that is shown here, in which we are trying to find the first one of a set of conditions, conditions 1, conditions 2, conditions 3, conditions 4, and so on, we're trying to find the first one of this set of conditions that holds. This is a bit overkill because we have all this noise, so to speak, syntactical noise, all these else's and thens and these ends. And so in Eiffel, instead of this nested structure, we have something more flat. Indeed, to understand the previous structure, you might think of a Russian doll, a matryoshka as it's called, with a big doll that contains a smaller doll, which contains an even smaller doll, and so on. Well, that's nesting for you. We may also want to use a structure that is more flat. Here the metaphor is more that of a comb, and the structure is going to be syntactically this. This corresponds to the plain case in which all that we are doing is looking at the set of conditions to see which is the first to hold. The order, by the way, is important. First we test condition 1, and if it's satisfied, we stop there. That's the end of the story. We execute instructions 1 and nothing else. Then we test condition 2. If it holds, we execute instructions 2 and stop. So the order is quite significant, and we stop at the first one that holds. So in that case, of course, the structure that we just saw does exactly the job, but it's a bit overkill, and we have a simpler syntax in Eiffel, which is using the keyword else if. So you can see the syntax is very straightforward. It's actually easier to read in this case, in this simple case, than the nested structure. If condition 1, then instructions 1, else if condition 2, then instruction 2, else if condition 3, then instructions 3. There is a new keyword, else if. As a piece of trivia, Eiffel, other than else if, only has keywords that are each made of a single English word. This is for simplicity and to make sure the syntax can be remembered easily. So we only have simple keywords like do, like else, like if, like class, which are simple and usually short English words. But there is one exception in the entire language out of the 64 or so keywords. That's else if, which is two simple English words coalesced into one, and that's because there is no plain simple English word that carries the connotation else if. So that's the structure that we have. We can think of it again as a comb. In the branches of the comb, we have the conditions, first if and then else if, except for the last one, which is just else. And between the branches of the comb, we have the compounds. Remember once more that each one of these instruction 1, instructions 2, and so on is not necessarily just one instruction, it's a compound, so it can be any number of instructions, including 0. This is in this more general form. If we want to be absolutely precise about what's possible, you see that there's always one condition following if, and then followed by a compound. The compound could be empty, of course, but this part is always there. Then we have 0 more else if branches. It doesn't have to be one. Our first variant didn't have one, but we can have 1, we can have 2, we can have any number, or we can have 0. And then there's 0 or 1 else branch. And one thing that we can notice here is that it's rather awkward as a way to describe the syntax. It's very informal. We will need a more mathematical way of describing syntaxes, the syntax of such constructs, and this will come soon with techniques for describing syntax mathematically, in particular what is known as BNF or Backus-Naur form. Our last construct is an alternative to the previous one. It applies to the case in which we would have an if-then-else, but all the conditions are of the same form. All the conditions are of the form is a certain variable equals to a certain given value. So the first one might be a equals 7, we do something special. Then if a is equal to 25, we do something else, and so on. So that's what we do. We always compare a particular expression, in this case a variable a, to possible values. And sometimes we might want to say if a is equal to 25 or a is equal to 23, then we do instructions 2. So in this case, there is a simpler way to express it with also a couple of semantic differences. We can use the inspect instruction, which says inspect expr, where expr is an expression. It has to be character or integer in its type, although there are a few more possibilities that correspond to types that we haven't seen yet. And I think the syntax is self-explanatory. When value 1, you can also list several values. You can also list an interval. This notation here with a double dot means interval, that is to say anything between value 4 and value 5. And so what this says is execute the first branch for which the value of expr is one of the corresponding values. Well, what I said would be true if the order were really significant. In fact, it doesn't matter because it is required with the inspect instruction that all the values be disjoint. So the order doesn't matter. This is the difference between an inspect and an if, then, else if, else if, else if. It's that with this if form of the conditional, we are going to stop at the first condition that evaluates to true and execute the corresponding instruction. So the order matters. 2 of the conditions could be true. In that case, the first one that we evaluate, meaning the first one that is listed in the instruction, will take precedence. With inspect, we can evaluate it the same way, but we don't have to because the order doesn't matter since it is guaranteed that all the values are different. And so this means that for compilers there are other ways to implement an inspect than just successively testing all the possible values. There are techniques which are actually faster than that go through tables. I'm not going to go into the details of this. Let me just mention that there are more efficient ways of implementing this, and you can try to think for yourself as to what an inspect table is and how it could work. So here's an example of an inspect instruction, multi-branch as it's known. We have a certain input character which is of type character. If that character is a letter, an uppercase letter, then we execute instructions 1. If it is a digit, we execute another set of instructions. If it's the hash sign, we execute instructions 3. You can see in the first two cases this use of an interval. A.z means any character between A and Z in the order of the alphabet of the character set, and 0 dash dash 9, there's an apostrophe here, you don't see it. It has to be an apostrophe, of course, because it should be a character. So this means any digit, 0, 1, 2, 3, anything between 0 and 9. And so this is going to execute instructions 1 for a letter, instruction, or at least an uppercase letter, instructions 2 for a digit, and instructions 3 for hash sign, and the other instructions for anything else. Now, what about if there is no else? So let's come back to the previous slide. There's an important property here, which is that if there is no else branch, and this part of the else branch is optional, then we don't just do nothing. That would be the case with the conditional. In the conditional, if there is no else clause, well, you see what happens. We are trying to find a condition that is true, but if we don't find any, we saw that it's okay to omit the else clause. In that case, the instruction does nothing. The multi-branch is different, because the multi-branch says I absolutely want one of the values. And if I don't want that, if I accept that the value of expert could be something else than value 1, value 2, and the values in the interval here, then I can always write else nothing. It's always possible to have an empty compound. But if I don't have an else, and none of the values match, then it's going to produce an error. It's not technically called an error, it's called an exception. What's an exception? Well, it's basically something that you don't want. It's good enough to remember that exceptions are bad. Exceptions are a bad thing. Exceptions are abnormal situations that arise at runtime. It's possible to recover from exceptions using techniques that you can read about in the textbook. I'm not sure we'll cover it in one of the lectures, maybe we will. But usually an exception actually causes the program to abort and terminate. So we don't want this. Okay, so this takes us to the end of this second sub-lecture of the control structures series. What we've seen is that because computers can branch, that's really something they can do based on conditions, branch meaning going in one of two possible directions, then we can take advantage of this mechanism to have high-level constructs in our high-level programming language that enable us to write algorithms that will do different things in different cases and take advantage of conditions. So we can have two or more branches. By the way, it's always two or more branches, because even if, for example, we have an if without an else clause, it's still two branches. One branch does something, the other branch does nothing. In general, we can have 2, 3 or more branches. We have two ways of achieving it. As you saw, we have the conditional instruction and we have the multi-branch, which are slightly different. And they have different requirements. The multi-branch applies only in the case in which we are comparing specific values of a certain expression. The conditional is more general than that, and there's also a different semantics for absent else clauses, nothing in one case, exception in the other case. So this is a very important set of mechanisms, and almost every algorithm under the sun has a conditional and often many, many different conditionals of some kind.